Okay, let us continue the third part of today's class. Okay, let us open go back to the slides. So, okay, we have talked to the third point. Okay, in the context of distributed resource allocation, the challenge in this case is that because secondary users are interacting through actions taken on their shared wireless environment, the rewards or cost functions that is seen by the secondary users has to share a common yardstick. Okay, what is the meaning of the word yardstick? Okay, let us see the handout. Okay, so problem 2, what is yardstick? Solution: a fact or standard by which you can judge the success or value of something. Okay, this means yardstick. Okay, yardstick for all the different types of traffic. Okay, about the word distributed. Okay, I think that you may have seen this word many times. Okay, so the opposite word of the distributed is centralized. Okay. So next, importantly, by providing a single common measuring scale for different types of traffic, the MOS. Okay, do you remember what is the MOS? Okay, let us review it. Okay, on page 51, MOS is the abbreviation of mean opinion score. Okay, the MOS metric provides the means to perform this integrated seamless traffic management and resource allocation across traffic of dissimilar characteristics. Okay, please see Dobrijevic et al. 2014. Okay. So let us see this. Okay, this paper. Okay, written by Dobrijevic et al. The title of the paper is QPoint, QoE-driven path optimization model for multimedia services. Okay, which was published in International Conference on Wired/Wireless Internet Communications in 2014. Excuse me. Okay, so let us go back to page 53. Okay, so do you know what is the meaning of this word seamless? Okay. Okay, sometimes I see a word, if it is easy for me, then I will not explain it in the handout. However, a word is easy to me is not necessarily easy for you. Okay, so what is seamless? That is without sin. Okay, if you see an English word end with LESS, okay, it means without this thing. Okay, without sin. Okay, so that is nothing between the two things. Okay, it's sinless. Okay, for example, if you are using your cell phone and walk from a cell to another cell, then your cell phone will execute the handover. Okay, handover. So that means your cell phone connect to the first base station and then change to connect to the second base station. Okay, But when you are using your cell phone, you will not be aware of this handover. Okay, for example, if you are talking to your friend or if you are watching video, okay, you will not be aware not be aware of any break, okay, or interruption of the communications. Okay, this means seamless. Okay, to advance in the presentation along these dimensions, we will continue to assume the same network setup described earlier in this chapter. Okay, for one more thing, if you want to know the Chinese meaning of seamless, then I can tell you, it means 无缝。OK， 无就是没有的那个无，缝呢就是缝隙的缝。Also this is an EMI course, that is a course which is taught in English. I think sometimes I can explain the Chinese meaning of some word. Okay, I think this is very helpful for you to understand the context of our slides. Okay, we will further assume that all primary and secondary links in the network transmit using adaptive modulation and coding, AMC. Okay, what is adaptive modulation and coding? Okay, please see the next slide. In AMC, the modulation scheme and the channel coding rate. Okay, do you remember what is the channel coding rate? Okay, if you forget it, please review the handout of chapter 2. Okay, if I remember correctly, I have introduced it to you. So let us see channel coding rate. Okay, good. Okay, here channel coding rate. So you can click on this channel coding rate. Okay, so it is problem 9. Okay, on page 15. What is channel coding rate? If you forget, you can review the solution to this problem. Okay, let us go back to the slides. Okay, in AMC, the modulation scheme and the channel coding rate are adapted according to the state of the transmission link, usually measured in terms of SINR. Okay, do you remember what is SINR? Okay, it means signal to interference and noise ratio. Okay, it is a quantity, okay, which is equal to the signal power divided by the interference power plus noise power. Okay, under these assumptions, SUs, okay, that is secondary users, can infer. Okay, what is the meaning of infer? Okay, let us see the handout. Okay, let us search for infer. Okay, next infer. Okay, good, here. So page 54, problem 1. What is infer? Okay, solution. To form an opinion or guess that something is true because of the information that you have. Okay, let us go back to the slides. So under this assumption, secondary users can infer the state of the primary link and maintain their cost interference to the primary network below a tolerable threshold. Okay, so you can see that secondary users cause interference to the primary network, okay, including the primary link and the primary user. Okay, if you forget, let us go back to the figure. Okay, let me see. Okay, figure 2.1. okay, you can see that it is the interference from secondary network to primary network. Okay, this and this are the interference to the primary network, okay, including the primary network link. Okay, and this is the primary user. Okay, we assume only one primary user in this chapter. Okay, so let us go back to, okay, I think maybe page 52. Okay, oh sorry, not this page, not this. Okay, yes, this page 54. Okay, so please see Mahamadi and Kwasinski 2018. Okay, so let us see, this is a paper written by Mahamadi and Kwasinski. Okay, the title of the paper is Neural Network Cognitive Engine for Autonomous and Distributed Underlay Dynamic Spectrum Access. Okay, this is an archive preprint, okay, which is in year 2018. Okay, when you see an archive preprint, okay, sorry, something call my phone. Okay, please wait me a minute. Okay, I think I need to, okay, good, I have blocked it, okay, because I'm teaching the course. Okay, when you see an archive preprint, for example, this is in 2018. Okay, then you can try to find the latest version of this paper. Okay, maybe this paper is already published in some journal or conference. Okay, so let me show you. Okay, so let me open the, okay, Chrome. Okay, oh, sorry, I need to close this app. Okay, so for example, let us try to search for this paper. Okay, neural network cognitive engine for autonomous and distributed underlay dynamic spectrum access. Okay, this is what we want. Okay, so you can click the first result. Okay, then you can see IEEE Open Journal of 2021. So it means that this paper is already has been already published in an IEEE journal. So let us click it. Okay, so you can see that this paper was published in IEEE Open Journal of the Communications Society. Okay, in 2021, and you can click on this button to download the PDF of this paper. Okay, let us go back to the slides. Okay, so let us go back to page, okay, maybe 54. Okay, good, here. So next page, when using AMC from Chu, please note that it is read Chu, not Q. Okay, Chu and Chara, okay, 1999. Okay, let us go to this reference. We can see that this paper is written by Chu and Chara, and the title is on the performance of adaptive modulation in cellular systems, which was published in IEEE Transactions on Communications. Okay, it is also a very good journal in the field of telecommunications in year 1999. Okay, let us go back. Okay, the relation between transmit bit rate and the secondary user threshold SINR is, okay, RIS is equal to W times log 2 of 1 plus K times beta IS. Okay, so we know that where RIS is the bit rate, okay, and where W is the bandwidth of the channel, okay, where M of beta I is equal to 1 plus K times beta I, okay, this term, okay, however, here the author omit the superscript parenthesis S, okay, here, is in fact the number of bits per modulation symbol, okay, and thus in practice takes only a small number of integer values. Okay, do you know what is the number of bits per modulation symbol? Okay, if you have taken the course Digital Communications, then you must know this concept. Okay, if you did not take the course Digital Communications, then let me explain it to you. Okay, in digital communications, there are many types of digital modulation. Okay, for example, BPSK, binary phase shift keying. Okay, after do the modulation, okay, the communication system will transmit bits, convert bits into symbols. Okay, so the capital M, okay, in digital communications, we usually use capital M to denote the number of bits per modulation symbol. Okay, for example, in BPSK, capital M is equal to 1. Okay, one symbol only has 1 bit. Okay, and in another digital modulation, QPSK, quadrature phase shift keying, okay, capital M is equal to 2. Okay, one symbol has 2 bits. Okay, and in 16 quang, okay, let me show you what is 16 quang. Okay, I know there are some students in our class that did not take the course Digital Communications, so I need to spend some time to explain it. Okay, so if for the 16 quang, where quang means the quadrature amplitude modulation, okay, you can see that, okay, this is digital 16 quang, okay, with example constellation points. So on the IQ plane, okay, I means the in-phase component, Q means the quadrature component. I think you have learned them in the course Principles of Communications. Okay, if you did not learn the course Principles of Communications, and if you do not know what I am talking about, okay, please send me an email and I will answer your questions. Okay, so we can see that there are 16 constellation points on the IQ plane, and each blue point, okay, represent a modulation symbol, okay, which represent 4 bits. Okay, for example, this point, this cancellation point, or this symbol contains the information bits 1011. Okay, so there are 4 information bits. And next, okay, similarly for the 64 quant, okay, this one, okay, 64 quant has 64 constellation points, and each constellation point is equivalent to a symbol. Okay, and in 64 quant, a symbol can carry 6 bits. Okay. Okay, and furthermore, there is also 20. Okay, here 256 quant. Okay, so why do I give these examples? Okay, because in the practical wireless communication standards, the common digital modulation we can see is BPSK, QPSK, 16 quant, 64 quant, and 256 quant. Okay, so in 256 quant, the number of bits per modulation symbol is equal to log 256. Okay, so we can compute this. Okay, 256 and take log 2. Oh, sorry, it is log 10. Okay, then I need to divide it by 2 log 10. Okay, which is equal to 8. Okay, good. Okay, so back to the slides. Okay, so for the 256 quant, capital M, the number of bits per modulation symbol is equal to 8. Okay, so we say that in practice takes only a small number of integer values, and k is equal to 1.5 over negative natural log of 5 times bit error rate. Okay, BER means bit error rate. Okay, it is a constant that depends on a target maximum transmit bit error rate BER requirement. Okay, in digital communications, when we transmit some information bits, we need to control the bit error rate under some maximum value. Okay, under some target maximum value. Okay, so this is the target maximum transmit bit error rate requirement. And what is bit error rate? Okay, it is a very important terminology in the field of communications. Okay, bit error rate means it is a ratio. The erroneous bits, a number of error bit divided by total number of bits. Okay, so it is the bit error rate. For example, if you transmit, okay, let me show you. Okay, if you transmit 10 to the 1 megabits. Okay, that is 10 to the power of 6 bits, and the number of error bits is equal to 100. Okay, then the bit error rate is equal to 100 divided by 1 megabits. Okay, and which is equal to 0.0001 which is equal to 10 to the power of negative 4. Okay, like this. Okay, it is 25 minutes. See you next time. Goodbye.